In this lesson, we will introduce the topic of solving sets of linear algebraic equations. Many problems in engineering involve solving sets of linear algebraic equations. Here is a set of three equations with three unknowns. 2x1 plus 0x2 minus 4x3 equals 9. 0x1 plus 2x2 minus 2x3 equals 8. And x1 plus x2 minus x3 equals 7. All three equations have a form in which the unknowns x1, x2, and x3 are multiplied by a coefficient and appear on the left side of the equation, while constants are placed on the right side of the equation. Notice that there are no terms in which the unknowns are squared, raised to negative powers, or multiplied with each other. These terms are not allowed in a linear equation. The unknowns will only be raised to the first power. We can rewrite these three linear equations into a single equation using matrix notation. On the left side of the equation, the coefficients are placed in a square 3 by 3 matrix. 2, 0, negative 4, 0, 2, negative 2, 1, 1, negative 1. The unknowns are placed in a column vector to the right of the coefficient matrix, x1, x2, x3. And the constants are placed in a column vector on the right side of the equation, 9, 8, 7. Notice that we can regenerate these three linear algebraic equations from the single matrix equation by following the rules of matrix multiplication. We will call the coefficient matrix capital A, the unknown column vector capital X, and the constant column vector capital B. So our goal will be to solve the matrix equation AX equals B. When discussing methods of solving sets of linear equations, it will be more convenient to use a general notation for the coefficients and constants, so we will use lowercase a to refer to the elements of the coefficient matrix. Each element has two indices. The first index identifies the row, and the second index identifies the column. In this example, the element in the second row, third column, A23, is -2. We will use lowercase x to refer to elements in the unknown column vector, and we will use lowercase b to refer to the elements in the constant column vector. Each element of the x and b vectors has one index to indicate the row number. For example, the element in the second row of the constant vector, b2, is 8. In general, there will be n equations and n unknowns. A is an n by n matrix containing n squared known coefficients. The unknown x vector contains n unknown values. And the constant b vector contains n known constants. If we have a small number of unknowns, we can find the solution easily through direct substitution. Let's look at a simple example in which we try to determine the price of two fruits. One person purchases 2 apples and 1 pear for $4. A second person purchases 1 apple and 2 pears for $5. We want to determine the price for an individual apple and an individual pear with this information. Let's call the price of an apple x1 and the price of a pear x2. For the first person, 2 times x1 plus 1 times x2 equals 4. For the second person, 1 times x1 plus 2 times x2 equals 5. Since we have two equations and two unknowns, we can find a solution to this set of two equations. If we convert this set of equations into AX equals B form, we have matrix 2, 1, 1, 2 multiplied with vector x1, x2 equals vector 4, 5. However, since we are using direct substitution, it is unnecessary to use matrix notation. First, we solve the first equation for x1, and substitute the resulting expression into the equation for x2. We find that x2 is equal to 2, making x1 equal to 1. This means each apple costs $1 and each pear costs $2. It did not take us very long to solve this problem through direct substitution, but what if there were 50 food items instead of just 2? We would need 50 equations to solve for the 50 unknowns, and it would take quite a long time to find a solution through this method. Another method for solving AX equals B involves using the inverse of matrix A, which is denoted by A raised to the -1 power. We start with AX equals B and multiply both sides of the equation by the inverse of A. On the left side of the equation, the inverse of A times the matrix A is equal to the identity matrix. The identity matrix times any vector is simply the vector itself. So the equation becomes x equals the inverse of A times B, and we can use matrix multiplication to solve for x directly. This method requires us to know the inverse of a, and unfortunately the computational time required to determine the inverse of a is at least as long as other methods for solving ax equals b. So there's no real advantage to taking this route to solve a system of linear equations unless you happen to have already calculated the inverse of a for another purpose.